Hey everyone, I'm gonna get started. So I'm Patrick Roberts. I'm presenting when abstractions fix too much. So here's my other slide. So start with why this talk. I just want to say I've solved problems where performance is a correctness issue and not just a nice to have. I've used general purpose libraries where optimal performance needs to be achieved and sometimes cannot be achieved without re-implementing the entire abstraction that's provided in the library. This is a pain point that I attempt to address in this talk. Personally, I've built both specialized and general purpose libraries for various purposes. And through that experience, I've learned how to implement some techniques to make general purpose libraries more reusable in the context of special purposes where performance is a front end, like a first priority requirement for that library. And so I want to share kind of this toolbox of techniques that I've developed and show how this works in a general an abstraction. So as I said before, I'm Patrick Roberts. My experience, I've worked in embedded systems. From there, I would transition to modern C++ with low latency trading software. After that, I went into AI accelerators involving RISC-V device kernels. So kind of going back into embedded systems partially, but also there was a high-level part of the stack that was in OS code as well. Now I'm working for a company called StackAV that does autonomous trucking, and I work on their onboard infrastructure team. So I do a lot of the core infrastructure for the high-level AI development that's done on top of that. I'm also a co-author of the AnyView proposal, P3411. It's currently active, and I also love fractals and template metaprogramming, so just something that's always interested me. So let's start with a core tension of abstraction. Robert Martin defines abstraction as the elimination of the irrelevant and the amplification of the essential. So I want to talk about contextually what irrelevant means. You want to lift your level of expression to what it is you're trying to express in your logic. Like if you're writing code that is an algorithm, you want to state that algorithm by name. You don't want to write the implementation of that algorithm by hand because it becomes harder to maintain and so on. And so you eliminate the irrelevant implementation details by lifting your level of expression to an abstraction. And the question I want to ask is, well, when you define it this way, what it's irrelevant to whom exactly? And so I bring up an example of vector pushback. It has a contract that it's amortized constant time. And in the event that it's not constant time, it reallocates the entire collection and moves all of the elements. And that's an implementation detail when it decides to do that, depending on how vector implements its reallocation strategy. And it doesn't expose that detail to you because it's an abstraction. That's something that it makes irrelevant to the user. But some users are performance conscious and they need to know exactly when that reallocation happens. And so either they rely on knowledge of the implementation in order to guarantee that allocation doesn't happen, or they have to reserve in advance explicitly to ensure within the context that they're not paying for the non-constant cost of reallocation. But even then, with that contextual knowledge, you're still paying for the cost of the branch where it's checking, does it need to reserve more memory? So regardless of whether you've ensured that it's necessary or not, you're still paying for that branch. So before I move on, I just want to say the standard library has addressed this in part, with the new in-place vector proposal, they've added a larger variety of capabilities to it, like unchecked pushback, and to address these performance concerns where, in a performance critical context, which in-place vector is intended for, you give more control to the user in terms of what guarantees that they want the library to enforce and which ones that they're assuming responsibility to uphold. So more chances for UB if they're not careful, but at the same time they get more performance out of it. But again, you have to wait for the standard library to release abstractions that do that for you, and sometimes you can't wait that long, and you need to implement your own abstractions to work around the limitations in general purpose libraries. So another example, you have vector, basic, string, polymorphic. They all have a particular storage policy that they implement based on allocators, and sometimes in a performance critical context, you might not want to allocate your memory, or in the case of basic string, it has small buffer optimization that has an implementation defined buffer size for before it falls back to allocation once that size is exceeded. If you wanted to change what that implementation defined limit was for the small buffer, you'd have to implement your own string. And so all of the capabilities that the basic string abstraction provides from the standard library, you'd have to re-implement yourself in order to do that. And so, and the reason is because the storage is not exposed as a policy. It's not customizable. So, and that wasn't the original intention of the library, but users have special needs for performance requirements, and sometimes that abstraction works for them except where performance is concerned. And then lastly, AnyView. There's a lot of things that you might want to customize about this, but that the standard library proposal and its implementation has to make a choice for you, because as an abstraction, it needs to simplify things. And so some of those choices involve like the underlying representation, the dispatch implementation, how that's facilitated, and then even the semantics, like does AnyView have a moved from state? Is that moved from state valueless? Does it have guaranteed semantics? And that was something that was debated even within the committee, and the decision was that we don't want a valueless state because AnyView is a range, and range has a reasonable surface for defining default semantics of an empty range. And so because empty range is kind of a reasonable default state, they decided that there should not be a valueless state. And so, some users might not want to have a default state and pay for destroying the move from object at the point there where it's moved from. And so, there are some performance considerations that there's a trade-off between the guaranteed semantics and the guaranteed semantics and whether the performance is something that you care for. Like in the case of the move from state, you're getting additional semantics and guarantees about the move from state that you might be paying for that without needing it, because a lot of people in modern C++ especially kind of have moved away from the idea of actually using an object in the move from state. It's usually discouraged, so why bother defining the semantics around that if that has a performance cost? So all of these can be potentially converted into policies, and so this is sort of a toolbox for mechanisms that can be turned into policy-based design. And so I have several examples in what the code looks like and how it looks in the usage as well. I don't know if my pace is good or not, but like if I'm missing any context here, feel free to raise your hand and ask like what are you talking about, and I'm fine to clarify anything. So I gave a talk last year on AnyView and the design decisions behind that abstraction, and so I'm assuming a little bit of knowledge about what AnyView's purpose is in this talk, and if some of that is not clear, like yeah, you should definitely ask, and that's fine. So we'll start with a capability here. In this case, we're defining the capability called increment. the base class is describing kind of the shape of that capability. So it's a unary capability, which means that it has one receiver argument. So the receiver is the incrementable. The arity is not referring to the total number of arguments, but just the number of receivers that exist on the capability. This is distinguished by, what is the thing that you are type erasing? So in this case, like, you're type erasing the incrementable and providing an abstraction that provides this capability. So in this case, yeah, you just increment the object, and that's your implementation. So you'll note the increment capability itself doesn't have a template parameter, but the function itself does, and that's kind of an important thing I'm going to be playing around with in more examples. So what this looks like in a type erase concept, or a type erase context, you have an existential type and an increment, or it defines an increment operator, and then you have this this thing that's called dispatch. You give it the capability that you want to dispatch to, and it will invoke that implementation. I'm going to cover the mechanics in a lot of detail here. This is just to give a kind of a snapshot of what the usage point looks like. So another one, a binary capability. In this case, you have two receiver objects, self and other, and you compare the values. So in this case, the intention is to type erase the objects that are intended to be passed to both parameters. And those of you that are familiar with Rust traits and DIME compatibility, there's this idea of some traits can be type erased and others can't, and their shape determines that criteria. So in this case, like a binary capability, you might be erasing two different concrete types, and the problem with that is this is a single dispatch, so it has to choose one concrete type to create a closure around. You cannot just have the cross product of all combinations of types. That's not how single dispatch works. So you have a choice of, well, do I have a finite amount of types that I work with and do the cross product globally across all of them, essentially implementing a double dispatch, or do I provide some fallback semantics that kick in when the concrete types mismatch? And so in that case, if they do mismatch, you need to provide some sort of default behavior to make the type erase capability a complete function instead of a partial function. So in this, in the existential type, you would define an equality operator against other, and then the dispatch would take the this and the other as two parameters, and the dispatch implementation would reify the other type to check its identity against the this type being dispatched on. And if they do match, then it delegates to the implementation. Otherwise, it delegates to the default value. And so the default value is an additional piece of information that's required to make that an erasable capability. So another one, a nullary capability, one that doesn't take any receiver arguments. And it's kind of interesting because you still need a receiver in the type erase case to actually dispatch. But once you've dispatched to the implementation itself doesn't have a receiver. It just does some sort of thing that's based solely on the type, and it doesn't require any value information about that type. So in this case, we're just querying the type ID of an object, and that's what this capability is intended to do. So yeah, you might define a type member function, and in that case, you would dispatch on the identity passing the this, which is the existential type, which is used to look up the implementation. But once that implementation is dispatched, it doesn't take any parameters. So moving on from capabilities examples, I'm going to get into the dispatch mechanism itself. And so we'll define some things that we're going to build on. We define a type alias template called signature, and it decltypes the signature of the capabilities function template instantiated with a particular concrete type. Getting that function signature is important for being able to define the type erasure when you dispatch. And so a primitive that we define here is bridge. And what bridge does is it takes a capability, a concrete type, T, and then the signature is used to help with avoiding the need for argument deduction. Because when we erase a capability, we don't want to deduce arguments. We want to specify what their arguments are. They're fixed, and you need a function pointer with specific arguments. You can't have something like a functor or lambda that deduces arguments. And then we define a value template called dispatch that I showed in the examples previously that takes the capability. And then here I default it to a type trait that deduces the concrete type from the receiver parameter. And then that's used to determine like how the dispatch is routed. Bridge is intended to be specialized for specific capabilities or specific kinds of concrete types. And it's intended to be kind of a unified syntax for dispatch, because this dispatch allows supporting both static dispatch and runtime dispatch. It implements both at different phases in the dispatch mechanism. So with dispatch implementing the runtime binding, we define a thunk that inherits from the capability, and what that does is it exposes the same function template from the public base class that we can pass to the signature. In addition, it allows you to annotate this capability with a concrete type that you want to dispatch it to. Yeah?
Sorry, can you just explain what dispatch is in context of capability? I don't think I really understand how it's
Sure. So capability describes a particular function that you want in an interface for something, and then the implementation provides like how that interface is implemented for a particular concrete type. That is sort of like a package thing, and then when you erase it, it's part of an interface of a existential type, and so this thing is responsible for holding a concrete type whose type is not known in the context where the existential type is used. And what dispatch does is it routes the interface of that capability from the existential type to the concrete type's implementation, and giving it the concrete type that's stored and erased within the existential type. Does that make sense?
Yeah.
Okay. So yeah, with the bridge, what we do here to create a binding is, instead of passing a capability directly, we pass a thunk. And what this says is we provide an implementation of dispatch over a capability for a particular concrete type T, and then we actually don't invoke the notion of the existential type here yet. This involves another thing called storage, which I'll get to in just a moment. But then what this does is the storage itself doesn't like inherently implement this capability. All it's responsible for doing is storing some concrete type. And the concrete type is responsible for providing that implementation. But the way that the storage gets access to the concrete type is through this binding. The binding tells you that T is stored in it because it dispatched to the specialization of this thunk. So it creates a closure around the concrete type that you can use to recover it from the storage. And so here, the storage self, we access the concrete type from it and then pass that as a receiver to the implementation that's dispatched to statically. So that this dispatch here is actually a static dispatch but it's creating a closure that's delegated to from a runtime dispatch, which I'll get to as well. So here's another example where we create a thunk over a binary capability. And so when I talked about DYNE compatibility earlier, the idea that you have to check the identity of the concrete type to make sure that they match, otherwise have a fallback behavior, that's what's happening here. So you receive the two concrete types, which are, so self and other are actually like CVRef qualified storage. So with the signature, you're given the concrete type, which is storage. That's always an object type, so like a PR value. But self and other can be CVRef qualified, or qualifications of this type. So both of them, if you remove CVRef, they're going to be the same as storage. But then what we do here is we dispatch on the identity capability for the other. So we're doing a runtime dispatch to figure out what that other's concrete type is that it stores. And if it's not equal, we fall back to the default value. But if they are equal, then we know that self and other both hold the concrete type T, and we can access that from the storage and then do the static dispatch on the capability delegating to the implementation, not through a function pointer, just through invocation of a function that exists in a partial specialization of the bridge class template. So storage, here's what its shape is. If you implement a storage class, you need one constructor template that takes a concrete type and then stores it in some unspecified way within the storage object. And that's why there's a policy, because the mechanism with which you store the object is actually really interesting, because it has a lot of trade-offs between the generality that storage is able to provide versus the performance trade-offs. And so you might make it less generalized and better performing within that constrained subset of use cases, or you might cover more use cases but sacrifice performance because you have to be able to erase more kinds of types that are less constrained. So I show a copy constructor and a move constructor here as well. Note that they're both tagged, and the reason why is because the storage doesn't actually know what it stores. Whoever knows what it stores is going to be the closure that requests the type that's stored within it. And what this does, it's a nice separation of concerns. It can focus exclusively on the mechanism for the representation of that erased concrete type, and it doesn't need to manage anything else. So when you do copy it, a closure needs to tell it what concrete type is stored within it so that it knows how to copy itself, or how to move itself. And then similarly, we don't really have a typical destructor. We have a tagged destructor called destroy as. And so when a capability informs the storage that it needs to be destroyed, it will invoke its destroy as function, so it knows how to destruct the concrete type stored within it. And then just accessing the concrete type for dispatching, we have some overloads of unchecked get. In this case, we assume like deep const semantics, where if the storage itself is const, then the concrete type that you're retrieving is also const qualified. That's not necessarily true for all kinds of storage objects, but this is just kind of the what am I trying to say? It's kind of the most expected use case is the deep const semantics. And if you look at the implementation for the newer library implementations for indirect or polymorphic, they have deep const semantics as well, because this behaves nicely in the context of value-based programming, where you treat it as a value rather than a smart pointer, and you get some nice behavior out of that. But like I said, it's not necessarily the case for storage, but it usually is. As a counterpoint, the first one I want to show here is allocator storage. So this takes a template parameter of the allocator, and so that decides, like, you want a PMR allocator, a std allocator, an offset allocator. Is that the right term, offset allocator? The Boost has like offset pointers, and you might want to use one of their allocators to store an offset pointer instead of a raw pointer. And so it takes that as a template parameter, and then what it stores in the class layout is a void pointer, whatever that means to that particular allocator specialization. And that this kind of emphasizes the point that storage is always dealing with a type erased object. It's not intended to deal with like an object with normal semantics. Okay, another example, in-place storage. So this is not a fully generalized storage policy. This is a constrained one. It can only erase concrete types that satisfy the size and alignment requirements specified by the template parameters here. And so this is the trade-off I was mentioning earlier, which is, you might want to have full generalized support. This is not capable of that. You have to choose an upper bound for your size and alignment, and any concrete type that you want to erase, if it doesn't satisfy that, you just have to reject it. And so that can be a constraint. It could be a mandate, which it turns into a static assert. So you can kind of choose whether you want spine or just compiler error, or maybe you want undefined behavior and you don't want to constrain it at all. I don't know, but yeah.
When you say you can choose, it gets to a question I've had since one of the earlier slides, but I've been waiting. Is this basically what you're describing, generic tools that you're advising us to kind of use, or is this part of a generic set of a tool set that works together that can be used?
I would say it's more of the former. I have been experimenting with all of these mechanisms in an open source library that I have on my GitHub account. It's not up to date with everything that I have in this presentation. That's something I plan to update in the coming weeks. But yeah, it's more of an advisement, I guess. And not everything that I'm discussing here is like super closely related. Some of these things I just kind of figured out separately from each other, and I just, through my experience over the past year, I found that they tend to work well when composed in this way. And I'll leave it to your opinion whether you agree with that. So maybe you don't agree with that. Yeah.
So I guess I'm sort of sensing a theme that these are sort of like interoperating type erasure techniques, and so far we've had type erase dispatch and type erase storage, and I think there are a couple more coming based on the opening slide. Is this something? And I'm sorry, I'm one of the people who's less familiar with the AnyView.
Yeah.
Does this like play into AnyView? Is AnyView specialized over these policies?
Yeah, so like I mentioned to Jody a second ago, I've been playing around with these mechanisms in an open source library that I've been developing over the past year. And a lot of these ideas I've figured out how to apply to the implementation details of the AnyView reference implementation that I maintain, and kind of use that as a proof of concept. Do these work out in something that's meant to be production worthy? And my experience is that they do scale well with the complexity of the type erasing mechanism, and there are many optimizations that I've implemented for AnyView, all very orthogonal and requiring like non-uniform representation, and so yeah, like there's a lot of weird requirements to enable these optimizations, and I'm trying to establish like a set of tools that help us gain a path for being able to enable those optimizations. Okay. So yeah, with the in-place storage, just to recap, it's not a fully generalized storage policy. It's only capable of erasing concrete types that satisfy those requirements. And again, you can choose whether you want to use FINE or some other constraint mechanism for rejecting the ones that don't work. And so that's the trade-off. And then kind of building on the two previous storages, you can also have a small buffer optimized storage where you use the in-place storage, and assuming that it uses FINE to bail out of the support, you can fall back to allocator storage for types that don't fit within the class layout of the in-place type. Yeah?
Given that, from what I know of your stuff here, it's all context forgivable.
Yes. There's an asterisk to that.
Okay.
The allocator storage is constexpr, the small storage is constexpr. In-place storage is not constexpr because you cannot do that as of C++26. I don't know if that's ever going to change, but the problem with in-place storage being constexpr compatible is that you have a byte array. You have to reinterpret cast that to the object pointer type that you want to placement new. And then assuming that you could somehow get around that, you also have the issue of having to reinterpret it later when you're retrieving the storage back, with the concrete type back from the storage.
Yeah, so I was going to ask, like, with this slide and the previous slide, I assume, like, in order to get it working in constexpr, it has to be, what, C++20, is that right?
C++20, yes.
Yeah.
Yeah, because it does rely on constexpr allocator support in order to do that. And it's, I forget the term that it uses for allocation at compile time, but it's like ephemeral. It's not actually allocated to something that persists at runtime. It's just within the compiler's interpreter. And so with small storage, in order to make it constexpr capable, what you have to do is you kind of have to have a if const eval split between what you do at runtime and compile time. So in compile time, you have the additional constraint that you just do not use in-place storage at all. But at runtime, if the object is movable and it fits the size and alignment requirements, then you can use the in-place storage. And yet, I can see your face. What this it does create a kind of a divergence in the mechanism that you use. And something I haven't really talked about yet was that the storage, like, there's no thing in the representation of the storage that says I'm storing it with this particular strategy. The strategy that it's stored with is actually determined by the closure, and so the closure actually knows how the object is stored. And if it invokes it at compile time, it's always going to be allocated storage. If it invokes it at runtime, the concrete type that it knows it's captured within the closure, it has all the information to know whether it's stored in place or allocated. So you don't need a tag on that union in order to retrieve it. It's just correct by construction.
What do you mean the closure knows? How could anything other than small storage know where the thing is stored?
So going back, this is the simplest example. The specialization of bridge here over the thunk of the capability, the thunk captures the concrete type that you're going to delegate this binding to. And so this partial specialization creates a closure over the type T that's known by the function pointer that you'll obtain from this static fin. So once you turn that into a function pointer, it's a function pointer that knows the type T, and then when you go to invoke it later, you'll ensure through construction that that function pointer is only accessible if the concrete type T is actually stored in the storage. And that relationship is sort of guaranteed by construction. So that's how the closure is able to know the concrete type that's stored.
That's how it knows the type, but you said it knows whether it's stored in the small storage or the allocation. I mean, it's just calling unchecked get, right? So
Yes.
It's storage to know what that means for that type.
Right. Okay. I see your point. The unchecked get implementation is a function template over T. The small storage within that template instantiation of the member function does have the strategy for does it retrieve it from the in-place storage or the allocated storage. So yeah, strictly speaking, yes, the small storage does know where it's stored given a type T, but without instantiating that function template, it doesn't know outside of that. And that function template is instantiated by the closure around the capability. Does that make sense?
Yeah, I don't understand how you're describing it, but I understand how it works.
Okay. Maybe I'm not describing it very well. Okay. Okay, I covered small storage. So here's some capabilities that are particular to storage. So I mentioned before that we have a tagged member function to destroy the concrete type in the object. You create a capability to do that, and now this capability is actually templated on the storage or the storage type. So for a given storage type, the capability implements the destroy as, and so you actually have two templates here: the one over the storage on the capability itself, but then you have the template over the concrete type. And notice the concrete type is not used anywhere in the function signature. That's very important because like that's what creates the closure. Like you have a type T known to the function pointer. The signature doesn't indicate anything about T, so you can use that on a type erased object. But then its implementation knows how to retrieve the concrete type. And that implementation is the same for all concrete types for the destroy specialization for a given storage policy. So that's why the template parameters are in two different places. I'm not sure if okay, so yeah, here's where you use it in context. If your existential type has the destructor, in the destructor you invoke this runtime dispatch over the destroy capability given the storage that it uses, and then the dispatch will perform the runtime dispatch to retrieve the function pointer, invoke it, and then because that is initialized by something that knows the concrete type stored, it will invoke it with the correct concrete type. So in addition to destroy, there's also copy, and there's also move that I'm not going to show, but it works very similarly. In copy, you have the template parameters in the same positions, and instead of just invoking the destroy as function and returning void, you invoke the tagged copy constructor on your storage policy, and that knows how to recover the concrete type and then copy it and then store it in the copy of storage that is returned from the function. So this allows you to type erase, copy, and move over a particular storage policy. And then, yeah, here's where you use it. And this is the interesting thing I noted about kind of a syntactic difference between C++ and languages like Rust. In Rust, it's a lot more clear that the capability to copy something is the capability of the object being copied, not of the object being constructed from that copy. Whereas in C++, syntactically, the implication is sort of yeah, you have a copy constructor, and syntactically, it's sort of implied that that's a capability of the target object, not the source object. But there's this weird kind of dissonance between the syntax and how the dispatch mechanism works, where you notice you're actually dispatching on other, not on this, because it is a capability of other. I always thought that was kind of a strange thing. I never really questioned that syntactic choice in C++ until I was working on these mechanisms and realized that there's kind of a dissonance there.
Do you have to do it this way? Could you copy and then dispatch what you copied?
You could, but the thing is that function pointer still comes from other, so other is the source of truth. The object that you're initializing doesn't own anything yet. It has to get that information about the concrete type from somewhere, and that information comes from other.
Okay, fair.
So yeah, another mechanism here is composing interfaces. So I'll introduce a primitive here called compose, aptly. and another one called iFace, which is similar in structure to Bridge, but instead of connecting a capability to a binding, what this does is it connects a capability to an interface. And so now this is the way that you introduce like your syntactic layer on top of the dispatch mechanism, which has the unified syntax for runtime and static dispatch. And now you have like syntactic sugar over that unified dispatch behavior. And so the two specializations here are just showing that like you can have a single capability or you can have a composition of capabilities that it expands into multiple base classes. And so you can compose an interface from multiple capabilities. And this is how this general type erasure starts to scale, and with the complexity of the abstraction is you're allowing you the ability to compose over multiple capabilities and not just a single one. That's essential. So here's an example with the increment capability that we covered at the beginning. You specialize iFace on the increment capability, and you expose the increment operator in the body of that specialization. iFace acts as a CRTP base class for an existential type. So the self is actually the derived class of this iFace specialization. And then you get this nice thing with the C++23 explicit object syntax where you don't have to deduce the derived type. It's fixed. And so when you invoke it, you don't have to do the internal static dispatch that you would have to do before C++23. Sorry, not static, static cast. The static cast that is required for CRTP before explicit object parameters. So it's just a nice little syntax that works well with CRTP base classes. And then when you dispatch, you just delegate to that sort of customization point, and that handles the semantics, whether it's like runtime or compile time dispatch. So I said that iFace is a CRTP base class of an existential type. That's not necessary either. It could be a CRTP base class of any type that implements this capability, whether that's a concrete type or an existential type. And that sounds weird because you would expect that the concrete type already has this syntax. But if you want to compose at compile time instead of with runtime type erasure, let's say you have an annotated reference wrapper type, and you want your reference wrapper to have all of the same syntax as the type that it references. You could attach a list of capabilities to that tagged reference wrapper, have it inherit from iFace, and then statically dispatch all of those capabilities to the underlying type through this mechanism. And there's no runtime polymorphism there. It's all static and compile time dispatch, but you still get this nice composition of abstractions where reference wrapper doesn't really need to inherently know about all these semantics. It just obtains them through the CRTP base class to expose the interfaces, and then that delegates to the dispatch customization point that implements all of these partial specializations for concrete types that actually do implement the behavior.
You say base CRTP base class. One thing I don't see here is the base class.
This is the base class. The derived class is not shown.
Oh, okay, so you derive from this thing.
Yes.
And the derived class is the self.
Yes.
Okay, then yeah, that's what I thought. Then the next question is, how do you compose? If you have plus plus and minus minus, in order for you to compose correctly, the final type has to be passed in both times, not the intermediate type.
Yeah, and that's why these two specializations exist, is because you can compose over multiple capabilities, and then when you inherit from the iFace, it's iFace of compose of multiple capabilities, or a type that inherits from compose if you want to shorten the type name. And then what that does is it expands to multiple CRTP base classes, one for each capability that exposes its own separate syntax. That expansion is done here on this last line.
Okay, could you show iFace again?
Can I show what?
iFace?
Oh, the partial specialization?
Yes.
Yeah.
Okay.
So this is one capability, but
Right.
But yeah, if you had multiple, then they can be multiple base classes of the iFace over a compose of capabilities.
So some kind of privileged access would be required to actually do this, right?
Well, they're all base classes of the derived class, so they already have privileged access.
The base class doesn't have privileged access to the derived class unless.
It does. All right, we can discuss that offline. Moving on, so witness tables. This was something that I discovered the nomenclature for recently. In structure, they behave very similarly to v-tables, but conceptually, they're a bit different than v-tables because v-tables describe a mechanism. They don't describe kind of the conceptual role that it plays. With a witness table, the idea is that this is a proof that a concrete type is stored within the erase type that implements the capabilities that are expressed here. And so if you have your witness table instantiation, that's proof that all of the capabilities are implemented because the function pointers are populated. But that also happens to be the mechanism through which you dispatch to obtain the concrete implementation. So, like I said, mechanistically, it's like a v-table, but it's a bit more conceptual than that. The other thing about witness tables is they don't belong within the class layout of the concrete type. They go outside of the class layout of the concrete type, so they're external to it. And then, so yeah, I kind of skipped over this quickly, but it also has the same partial specializations to compose over multiple capabilities like the iFace did. And then these are value templates. Oh,
So what's the purpose of the witness table? Because it seems like it's not necessary for the implementation to work because you have those context pointers, which were the function pointers originally, which can be accessed to actually perform the function that needs to be executed.
yeah.
So
They need somewhere to live. They live within the witness table. Like, so they're function pointers, and you can obtain them. They have to go somewhere, and they have to somehow be packaged with the storage that owns the concrete type that you're erasing, right?
right, well they have their storage when they're instantiated, right?
Mm-hmm. They're instantiated, but they just exist somewhere in static lifetime memory.
Yeah, and that's enough, right? Because
It's enough, but you still have to store either at least a pointer to it in the class layout of the existential type.
Okay, I thought the original dispatch was actually dispatching to that pointer that was in static storage.
What I showed before was the definition that you obtain function pointers from. I didn't actually show where they lived yet.
Okay.
This is where they live.
Okay.
Yeah, so I'm referring to the signature primitive that I shared earlier, which is an instantiation of the static fn, and that's stored as a pointer, an entry within the witness table. And then when you compose multiple specializations of witness for over a composition of multiple capabilities, then you have one entry for each capability. And so that's how it creates the table from these specializations. And then getting to the value template, note that like this is not templatized on a concrete type at all. It's only templatized on the capability and the storage object. The storage which knows nothing about the concrete type, as I said before. And so you get this uniform representation regardless of the concrete type that's stored within. And so with the uniform representation, you can store that in the existential type without having to specialize that per concrete type. But then where the concrete type comes in, you have these value templates that are like you're actually constructing the witness table for a particular concrete type. And so here we we declare a specialization of the witness table, and we say witness for concrete type T, and that initializes the entry with the function pointer obtained from the dispatch over the closure. So that thunk capability T, all right, I call it protocol, but yeah. This is the closure that captures that concrete type T and turns it into a function pointer that's stored in the table. And this is done at compile time when you instantiate the constructor template for the existential type over the concrete type T that's being constructed. So at that point that you instantiate that constructor template, that instantiates this value template to initialize the witness table like at compile time for that type T. And so it's kind of weird to think about because it's a compile time instantiation of a runtime mechanism. But the way that I think about it is that the translation unit has knowledge of the concrete type T, and so that translation unit instantiates the witness table for that concrete type. Outside of that translation unit, if you pass that existential type somewhere else, other translation units don't need to compile that witness table again. That's only done in one spot, but they can still use the existential type with the function pointers obtained from a witness table that is instantiated by a different translation unit. And so that's how the type erasure is facilitated. And so again, we have the other specializations that compose over multiple capabilities so that you're initializing multiple entries, one for each capability in the composition.
So if your witness table was not constexpr,
Mm-hmm.
then you would be able to modify the function pointers at runtime
You could,
and
yes.
change behavior dynamically.
Yes. I do not cover that in this talk, but it is an open question I've been thinking about for a while, and how you can scale that sort of mechanism in a way that behaves well, like within a composition. I haven't really figured out, like, inherently swapping out behavior at runtime is just it's kind of hard to contain that in a way that behaves nicely at scale. I haven't really thought through a strategy for being able to do that, but it is something I am interested in.
Yeah, it is. Yeah, so it's much easier than changing out the v table. So
Yeah, and like, because this is an explicit library feature, you do have explicit access to the vtable, unlike with virtual polymorphism, and so that exposes some interesting choices and mechanisms that were not possible with virtual polymorphism, as you said, with the runtime swap out of behavior. So this is a very basic like definition of what the existential type looks like, putting almost everything together that we've talked about so far. So you have an existential type that's templated on the storage policy and the capabilities, so that capability template parameter, it can be a single capability, it can be a composition of capabilities, and it works regardless. And so the iface exposes all of the syntactic sugar on top of the dispatch mechanism. And then the storage obviously has to live in the class layout, and that facilitates the storage of the concrete type. And then you have your witness table pointer that gets initialized by the constructor template that takes the concrete type you're storing. And so that's how everything fits together there. Going back a little bit to the bindings, I want to kind of like put this existential definition in context and hopefully make sense of how the runtime dispatch is facilitated. Oh, sorry, I didn't see that. What?
Yeah, can I ask, so back to the table, the point of the witness table. If the witness table is something you know statically how to make from the types, why do you need a pointer to it? That's confusing me.
Because it's only known statically within the constructor template instantiation.
Well, the
Once-
existential type is the holder that holds the erase type. Right.
Wait, sorry, say that again?
The existential type is like your stood and one, right?
Yeah.
It holds the erased type.
Yeah.
Got it.
Yeah, and so within the context of the constructor template, you know the concrete type, but once you've exited that constructor, that's completely erased and you're no longer in a context where that's statically known. You just have a pointer to an instantiation of a witness table. That type has no information about the concrete type, only the value template that you're pointing to knows the concrete type whose function pointers implement all of its capabilities.
But it's the function pointer implementation, the storage isn't there, so couldn't it be a static const expr and then not occupy storage in every object?
In order to be a static const expr, you'd either have to have a static const expr template, which you can't really do anything with, or if it's a static const expr non-template, then you have to template the existential type on the concrete type, which defeats the purpose. I mean, like, yeah, you could store the value template as like a static const expr within the existential type, but the thing is, like, the existential type eventually has more template parameters than just the storage and the capability.
I was hoping that was where you were going.
Okay.
Well, I've been thinking. So when you started, you were talking about how this allows us to have much more control over how type erasure is done.
Yes.
But also you talked about performance, and so none of this has showed anything about performance. So I was thinking about how do we manage the cache flip flop that you end up with virtual vtables and the extra storage space and things like that. So I actually thought you were going to go, and look, and we have no extra space for this. So that's why I thought one of those things was happening.
Yeah, I do have a section where I cover various optimizations that exist in any view based on these mechanisms. So hopefully that'll sate your appetite. Let's see, I covered that. Back to the binding in terms of the existential. So this is a specialization of bridge over null area capabilities, like dispatching from the existential type itself as the receiver. And so what I said before was that null area capabilities don't have a receiver argument, but in a race context, you still need a receiver in order to retrieve the implementation. But once you've retrieved the implementation, you pass through the arguments without the receiver. And so you can see, like, null array doesn't necessarily mean there are no arguments at all. You can have non-receiver arguments that are forwarded through. But in this case, we get the storage type out of the existential. We access the witness pointer and then resolve the base class that has the function pointer for that particular capability. And now that we've obtained the function pointer through a runtime dispatch here, that's what this arrow star operator, it's essentially a runtime dispatch similar to virtual dispatch. Then you can use that to invoke and forward through the rest of the arguments. Another neat thing about this is you're not limited necessarily on placing the receiver as the first argument. If you want to avoid the register shuffling that would be necessary to forward the arguments here from an offset of 1 to an offset of 0, you could actually place the receiver argument at the end and then just drop that off, and then when you forward the arguments through, it can just be a jump. So you don't have to do like the register shuffling to move the arguments over by 1. So like all of these things are now things that you're able to play around with by specializing bridge over a particular category of capabilities that you want to implement. Maybe your null area capability puts the receiver at the end, unlike the one here.
Why don't you always do that? Because the normal trick with type erasure is to force the tail call instead of argument shift.
You could always do that. It's just easier to read it here syntactically, like for slideware, putting the receiver as the first argument, it just makes it easier to read. But yeah, you might always want to do that.
For performance, you should always do that, because then you don't get call red, you just get jump.
Mm-hmm. Yeah, I haven't really thought through entirely, like maybe there's a use case where having it at the front still makes sense, or like one of the things I thought about was the stream operator, and it's a friend function where the receiver is actually the second argument. So there's some weirdness there, like where once you introduce the interface, you have some syntactic weirdness that you have to resolve by moving around the dispatch mechanism to put the parameters in the right place to turn it into a jump. So it's not necessarily always the ideal choice. It depends on the syntax that you're invoking the capability through.
The stream operator wouldn't have parameter back.
Yeah, it's a poor example, but I'm just trying to convey the idea. Like it's still dependent on syntax ultimately. Okay, yeah, and then so I showed the how the dispatch from the existential works to the function pointer, and then the function pointer is actually an instantiation of this static fn in this specialization of bridge. This one is a closure over T, so it gets the args and it dispatches to the nullary capability. I think I actually have an error here. Like it's supposed to recover T from the dispatch mechanism. I think I might have messed that. Like I think that's supposed to be comma T. But yeah, like now you're at a point where the type is statically known, and you do a static dispatch at that point once you've invoked the function pointer. So I have a diagram to try and like visualize everything that we've covered because it's a lot. And here I called it basic polymorphic instead of existential because that's how it exists in the implementation of any view. But it is effectively the existential type I've been discussing. So you have it templatized over the storage policy and the protocols or capabilities. That owns a witness table that's an instantiation or a pointer to the instantiation of the value template witness 4. And that takes the capability, the storage, and then the concrete type, which in this case is a view adapter. And it also has the storage in its class layout itself. In this case, view storage is a specialization of the small storage. So it implements the small buffer optimization with the implementation defined in-place size and alignment. And then when you do a runtime dispatch, you're getting the function pointer stored in an entry of that witness table. And that entry is a function pointer that exists in a specialization of the bridge class template. The function pointer is always going to be a specialization of bridge over a thunk. And so the thunk has the capability and then the concrete type that it's known to dispatch to statically within that implementation. And so that does two things. One, getting access to the storage, it requests the concrete type from that through unchecked get to get the concrete type. And then it also delegates with a static dispatch to the underlying implementation of that capability for the specific concrete type, in this case view adapter, and it just connects those together in a function invocation. So that's kind of the whole picture here. I'm gonna stop here if there's any questions, because yeah, that's a lot. Cool. Okay, moving on. So now on to some of the optimizations that this has enabled. In the AnyView implementation, there's been a lot of work, and I've highlighted 3 of the optimizations that I've implemented based on these mechanisms, and that this time last year when I presented on the AnyView design, none of these were possible, or if they were possible, the use of virtual polymorphism as the mechanism made them very difficult. Also you had to pay for the cost of a uniform representation that you have to abide to with virtual polymorphism. Whereas with this mechanism, not every specialization of the witness table has to have the same entries. Depending on the concrete type, you can actually customize what entries you have to erase capabilities for. And I'm going to go into that into a bit. So the first optimization that I implemented is what I'm calling an upcast conversion. It's not really an upcast because there's no inheritance of objects here. The inheritance actually happens in the witness table. But imagine if we have a composition of capabilities for a contiguous iterator that inherits from a composition of capabilities for a random access iterator, which inherits from a composition of bidirectional capabilities and so on. Whereas the base class witness table is just the set of capabilities for the input iterator. And so that's what this visualizing. So here's an example. You have one library that consumes a type erased forward view, and you have another library that produces a type erased contiguous view. Naively, if you wanted to implement this, you would note that the contiguous view models the forward view, and therefore it can be a concrete type that you erase as a forward view. And that would be a disservice to performance, because now every operation that you dispatch on that forward view would go through 2 layers of runtime dispatch, because one, to get to the type erased other any view specialization, and then that one dispatches to the underlying concrete type that it erases. And so you want to avoid this, and the way to do that is to support a sort of capability lattice where you can symmetrically transfer the storage and the witness tables and decay them to the set of capabilities that exist in the base class witness table. And so it's analogous to a base class conversion, but it's not exactly like it. And so the way that looks in this implementation, you have a specialization of the existential constructor that takes another specialization of a set of capabilities that is a superset of the capabilities on this type that you're constructing. And if it's a superset, that means that it inherits from it. So when you copy the witness table pointer, it's just an implicit upcast of that pointer type to the pointer to the base class witness table that implements the set of capabilities constrained. And so now you've actually just invoked the copy constructor on the storage. So you're transferring the storage of the original underlying concrete type exactly as it was erased in the original specialization. But now you have a view of it that's constrained only to the capabilities that this specialization of the existential type needs to implement. So now you have the ability to combine these 2 libraries without any runtime overhead. So it's still a single dispatch instead of double dispatch. Another place where this comes up is the iterator's witness table. So in any view, you actually have 2 existential types. One existential type for the view type and its capabilities, and another existential type for the iterator that you construct from the view type. So both of those are existential and erase a concrete iterator or a concrete view, respectively. And so when you implement the begin function on the view class, what you have to do is you have to implement a capability to obtain its iterator's witness table and its iterator's storage, and then you combine those into the existential type that packages them together. In this case, in order to support that conversion where different specializations can have the set of capabilities degraded from one point in the capability lattice to another, the function pointer has to return the witness table of the least amount of capabilities. So in this in this case, it's the capabilities for the iterator or the input iterator. So when we get this dispatch on the protocol T, what we're doing is we're actually obtaining a pointer to a witness table for input iterators. But within the context of this specialization, we know that that's actually a decayed base class of a more derived witness table. And so we actually downcast it to the witness table that implements the actual set of capabilities. This is sort of a limitation with this manually implemented mechanism, because like in virtual polymorphism, you can have a virtual function in a derived class with a slightly different signature than you have in the base class, and the language figures out how those upcasts and downcasts actually work, and it statically verifies that they're correct. and then performs them implicitly for you. In this case, because you're implementing the mechanism yourself, you have to do that downcast explicitly, and you have to implement the mechanism manually. So it exposes some implementation details that virtual polymorphism kind of hides from you. And this is the weirdness, is like you have to perform the downcast. But once you have it, and you know it's correct by construction, because you wouldn't be able to obtain it unless you're in the specialization of the existential type, then because that's guaranteed by construction, then you know that's correct. You don't have to check it. It's not a dynamic cast, it's just a static cast. So, okay. And then, here I show a dispatch on begin and also a dispatch on the iterator witness table. So I want to show what the dispatch on begin looks like first. So the begin capability, the concrete type is this view adapter type. So it holds a view type, and on that we call the ranges begin and end, and then store an iterator adapter that is the concrete type for the iterator's storage. So in this case, we actually store the iterator and sentinel kind of packaged together as a pair in the existential iterator type, because as I mentioned before, with the limitation of binary capabilities, you want a case where you don't have to do a runtime check to see that the concrete types match up. You would prefer to just have one receiver argument. And in this case, I'm creating a single receiver. That's the packaged iterator sentinel pair. So there is no double dispatch necessary or reification in order to check that they're compatible. It's just there's one receiver, and when you revive that concrete type, they're packaged together already, and so there's nothing to check. So that's why I packaged them together. And then the existential sentinel is really just an empty tag type that's used to facilitate the syntax of ranges capabilities. So like when you compare the iterator sentinel, like it's just to facilitate that syntactic layer, but not the dispatch layer. And then moving on to the iterator witness capability, this is how you retrieve the witness table for your type erased iterator. So there's a lot of template parameters going on here. Any view actually has several template parameters that are defaulted, but you can override. So you have the reference type, the R value reference type, and the difference type are three of them. And then you have this options, which is like a bit mask of capabilities that you describe implemented. So when you dispatch and obtain the witness table pointer, what you're doing is you instantiate the value template here and then get a pointer to it and just return that. It's doing a base class conversion to the input iterator table, and then in the context where it's known to be an alias of an actual derived class, you then downcast it again in that context. The reason that this uniform signature is necessary again is because in order to degrade the capability set, you have to have the witness tables for multiple specializations be the same type. In order to be the same type, they have to have the same function signatures. And the one that's in common is the most base class. So that's why that exists, is so you can just pass the witness table pointer from a derived one, or not derived, but from a more capable set to a less capable set. I realize I'm repeating myself, but it's a lot of detail to go through. And then here I made a reference to iterator protocol. So this is actually sort of a computed set of capabilities. And so depending on the options, if the options are contiguous, then we get the contiguous capabilities and then dispatch so on and so forth to whichever set of capabilities that are requested by the AnyView options. But wait, there's more. So I showed one dimension in that lattice. We're only degrading along one inheritance chain for witness tables. But in AnyView, because it's a bit mask of capabilities that are orthogonal to each other, you actually have this multi-dimensional lattice of degradation that you have to support. So the green arrows show like removing the copyable capability, and the yellow arrows show degrading the sized capability, like from size to approximately size to unsized. And you have to support degradation along both of these dimensions. But with a single witness table, you don't have a flexible enough representation to be able to do that. So in order to deal with that, I kind of lied about my existential type initially. I showed a single capability that is turned into a single witness table pointer. But in actuality, you have a pack of capabilities that are turned into orthogonal witness table pointers that can independently degrade capabilities from each other. And so when you convert from one specialization of existential to another, each of them are independently evaluating like whether they derive from the type and then degrade to the base class for each of them independently. So now you can have that independent conversion to a restricted set of capabilities along multiple dimensions.
How does it avoid combinatorial explosion? Your chart shows that if you remove like A, B, and that, or you remove B, A, you end up in the same place.
You do end up in the same place, yeah.
How is that done?
Well, because that same place is one specialization. The path that you do to obtain it is going through different specializations, but they ultimately reach the same specialization. Like when I show these,
do you have canonical order for them?
No, there's no canonical order. These arrows are just showing the conversions that remove exactly one capability from the set. Like there's arrows going all over the place that I don't show here because you can do a direct conversion if you want to degrade multiple capabilities at a time. This is just showing the lattice for one at a time.
Sure, but how do you ensure that you don't have a witness table for, let's say, CD and another witness table for DC, and they're different?
Okay, I see. Yes, the implementation specifies a canonical order, but that canonical order is not exposed to the user. It's an implementation detail.
But the implementation has canonical order.
Yes. Okay. Sorry. Thank you for clarifying. Yeah. So here's what the interview options look like. It's the bit mask, and so you look at how the bit mask is actually grouped, and you can see the different dimensions that emerge from the capability set. So you have one dimension for the input category, the iterator category. You have another dimension for the size capability, and then another dimension for borrowed and copyable. Borrowed doesn't actually need any function pointer to facilitate that capability. It just determines whether that specialization of existential enables the borrowed range value template that exists in the ranges library. If that borrowed flag is disabled, then it doesn't enable that specialization, and vice versa. There's no function pointer associated with that, but conceptually, it's still part of the capability lattice. And then here's the full capability lattice that the AnyView options implements.
So how many witness pointers are there? Because you said there were 4 capabilities, but you said 2 of them didn't require witness
borrowed does not require one, but the iterator category does require one. The sized and the copyable require one. But the thing about the iterator category is that that's actually the witness table of the existential iterator, not of the existential view. So you still effectively just have 2 witness tables in the existential view and 1 witness table in the iterator, and that's all you need to implement that full capability lattice. If you group your capabilities in a way that compacts the orthogonality as much as possible.
And so you said that the previous implementation, so I take it that you had this implemented before you used these capabilities, and you had this lattice implemented before as well?
No, the lattice was not implemented. You paid for the cost of downgrading by erasing the more specialized AnyView inside of the less specialized AnyView. And so you had that runtime dispatch when you converted. It's feasible to implement it with virtual polymorphism. It's very annoying, but the problem is that with virtual polymorphism, you also don't have the ability to customize that vtable representation for each specialization of any view. They all have to have the same witness table layout, essentially, or vtable layout, which is an unfortunate consequence of that design choice, or implementation choice, I guess I should say. Yeah, I don't expect you to try to read this. This was just to give a sense of the complexity. How much time?
10 minutes.
Okay. So another an optimization that I implemented was const conversion. So outside of the AnyView option bitmask, there's another dimension of capability downgrade that exists. So if you have a AnyView of int, you want that to be convertible to an AnyView of const int without paying for the cost of double dispatch. And it's possible to do that because you can have a const view of any non-const range. Like that's the purpose that as const view in C++ 26 implements. I forget if it's 23 or 26, but yeah. So essentially, you're allowing a conversion between specializations of any view to fulfill the semantics of as const view without paying for the cost of conversion. And so the way that I implement that, it ends up having to have two capabilities, one for each orthogonal witness table that exists in the existential view. So here we have like the capabilities associated with copyable, and then the other ones associated with sized. Copyable also implements moved and like the begin and end function, or well, end doesn't need to be type erased, but begin and all of the things associated with the mechanisms of dispatching to the iterator concrete type. So I package them together because they're not orthogonal. And when you degrade capabilities, like those are the things that remain constant. So you don't have to consider removing those orthogonally from the rest of the capabilities. So the way that I implement this optimization is I have a dispatch to obtain that copyable witness pointer and the size witness pointer, and then another dispatch to actually copy the underlying view from the storage. So that's 3 dispatches, but then the advantage is that once you construct the new specialization, all of the operations on that only have a single dispatch instead of a dispatch through 2 layers of erasure. There was something, oh yeah, there's also a move const, but I don't show it because it's essentially the same thing, but instead of copying the underlying concrete type, you move it. So closing thoughts, I hope I conveyed a sense of like the policy-based design that exists in this way of thinking about generalized polymorphism. The idea that like choosing mechanisms to unlock non-uniform representation can enable optimizations that would otherwise not be possible. The idea that as a library author, you should try to abstract transparently, and what I mean by that is like, yeah, the primary goal is to help the general purpose user get something as simple as possible. You want to, you still want to eliminate the irrelevant, but at the point that does not, or that's no longer irrelevant to like an advanced user that wants to optimize performance, you still want to allow an escape hatch into some form of expression that exposes these policy choices as things that can be substituted by an advanced user. And so the way that I facilitate this in my library is like, I'll have high-level type alias templates that fix policies to things that work in the full general context. So for example, I might use small storage or allocator storage so that I allow it to be used for all possible types. But I still expose the in-place storage if the user wants to substitute that mechanism and optimize performance for their special use case, they don't have to use that convenience alias. They can use the class template itself that exposes those as policies. And so you get both the flexibility for the advanced user and the simplicity for the general purpose user. And then also I wanted to make sure I conveyed the advantages that you get with this unified like the dispatch syntax, like being able to go through one customization point, regardless of whether it's a runtime or static dispatch. It allows you to express things that actually don't care how that dispatch is performed, and now you can use that interface for both static polymorphism and runtime polymorphism with it, and you don't have to re-implement it separately for both. And then some open questions that I think Jody and some others might have hinted at earlier. I still haven't quite figured out like how I want to express customizing constraints. So like, as I said before with the in-place storage, you might want to decide whether you use Sphene or do a mandate, which is a static assert within the body once it's instantiated. Or maybe you don't want to assert at all and you just want to fall back to UB or whatever for if something's not satisfied by a particular concrete type. I'm not quite sure how to expose that as a policy or whether it's even worthwhile doing that. As a library author, I don't want to assume that like there's no use case for that, because I'm providing a general purpose library and I want to support advanced use cases. There may be an advanced use case where it's necessary to change that. As I'm saying this, one thing that I just remembered is that was it indirect? The way that the indirect abstraction supports incomplete types is that some capabilities actually mandate the requirements instead of constraining on the requirements, because if you were to constrain, it requires it to be a complete type, and then you can't store it like recursively. So if you had an indirect where you're using it to build like a hierarchical self-similar structure, in order to deal with incomplete types, you actually have to make that a mandate instead of a constraint. And so that might be a use case for customizing that. Like normally, yes, you'd want it to be Sphene, but sometimes if you want to support an incomplete type, you might want it to be mandated.
Even by construction, correct by construction, you say what you want, you get what you ask.
Mm-hmm.
Okay.
Yeah. Capability resolution. What I mean by this is like, I've thought of scenarios where, some of the capabilities are inherently implemented by the storage policy. So for example, like allocator storage inherently implements the capability to move an object. In order to implement that, you just convert it to a valueless state and you transfer the pointer. And so that doesn't require a runtime dispatch for that capability. It's just something that can be statically dispatched on the storage type for the existential. But on the other hand, like maybe you're not intending for those semantics for move, and you would actually prefer to delegate to the concrete types move semantics instead. How do you customize the capability resolution there for the existential type? Like, how do you express whether you're intending to delegate to the storage policy or towards the concrete type that's being erased? That's still an open question I haven't figured out how to answer. Another one is like, I specified a particular relative ordering between the storage and the witness table, but maybe you want to swap those. One way you might facilitate that is actually putting the storage in a specialization of the interface and the witness table in a specialization of the interface, and then swapping the order of the composition for those capabilities would allow you to reorder those in the class layout. I haven't really thought about a nice way to do that and still be able to retrieve them generically through the dispatch mechanism, so that's something I'm still trying to figure out. And then finally, the witness table representation. I have some ideas for how to turn that into a policy. You might not necessarily want to point to it. Maybe you want to embed it in the class layout. Maybe you don't want orthogonal pointers. Maybe you want to do some sort of witness table multiple inheritance where they're not strictly orthogonal anymore, but you want capability degradation that takes advantage of that compressed representation and get better, like tighter dispatch with less indirection, like offsetting the pointer, etc. So these are policies that I'm playing around with in my library, and I haven't decided on a set that I want to expose in the library, but I'm also trying to keep it open-ended where users can implement their own policies to inject. So yeah, those are things that I'm like future paths for my library, and that's it. Are there any questions? Oh, no. All right. Thank you.
Thank you, Patrick.